The Jordan Show on YouTube.
All right, so today we're going to take a deep dive into something that might sound a little, well, old school, stack and heap. You might be thinking, wait, isn't that like computer science 101, like ancient history?
Yeah, you'd think so, right?
But before you tune out thinking this is all just dusty textbook stuff, I promise it's way more relevant than you think. Even if you're working with like the latest, fanciest programming languages.
You see, the thing about stack and heap is they're not just some theoretical concepts. They really directly impact how your code actually performs out there in the real world, how secure it is, even how certain bugs pop up.
Okay, so not just for like computer science exams then.
Nope, not at all.
All right, well, to be totally honest, I think I could use a bit of a refresher on what these actually are.
Yeah.
Just to make sure we're all on the same page.
Sure. So, think of the stack, right? Like a stack of plates.
Okay, I can visualize that.
You can only add or remove plates from the top.
Makes sense.
That's why we call it last in, first out, or LIFO.
Right.
And this is basically how your computer handles things like function calls and local variables. The last thing you added is the first one you got to deal with.
So the stack is all about like order and efficiency.
Exactly.
What about the heap? That sounds a bit more, I don't know, free form.
Yeah, you could say that. The heap is more like, imagine a restaurant seating system.
Okay, I like where this is going.
So when your program needs to store some data, it goes to the memory allocator. That's like the host of the restaurant.
Gotcha.
The allocator's job is to find a free space that's big enough for the data, mark it as reserved, and then give the program a pointer. Like, think of it as a table number, so the program can access that data later.
So the stack is for quick, tidy storage, and the heap is when you need more flexibility.
You got it.
Okay, I'm starting to see the picture here. But our listener sent in a bunch of sources that suggest understanding these concepts, stack and heap, is really crucial for certain types of programming, even today.
Absolutely. And that's where things get really interesting. Let's start with low-level programming languages. Think C or C++ Fin.
Right.
In these languages, the developer has a lot of explicit control over memory. Imagine you're at a restaurant, but you have to tell the staff exactly where to seat each person at your table, and then you have to clear everything away yourself afterwards.
That sounds stressful.
That's kind of what it's like working with memory in C or C++ way.
Oh, wow. So it's a lot of responsibility, and I guess a lot of potential for things to go wrong.
Exactly. Like, if you forget to free up memory you've allocated on the heap, that's a memory leak. And that can really slow down your program, even crash it.
Yikes.
And then there's the stack. What happens if you try to push too much data onto the stack?
I'm guessing that's not good.
It's like piling up too many plates. Eventually, you get a stack overflow and everything comes crashing down.
So low-level programming is like being your own memory manager. And it sounds kind of terrifying. Are there languages that make this a bit easier?
Oh, for sure. Modern low-level languages like Rust, they have features that help make memory management safer. But even with those, you absolutely need to understand the fundamentals of stack and heap.
So no escaping it completely, even with all the fancy new tools. What about high-level languages like Python or Java?
Yeah.
I feel like things are more automated there, right?
Yeah. In high-level languages, we have garbage collection. It's like having a magical cleanup crew in a restaurant.
So no more clearing the tables ourselves.
Exactly. You don't have to worry about manually freeing up memory. The garbage collector takes care of that. It finds memory that's no longer being used and frees it up automatically.
That sounds amazing. So does that mean we can completely ignore the heap when working with these languages?
Well, not so fast. Garbage collection is fantastic. It really helps prevent memory leaks, but it also introduces some unpredictability in performance. It's like you don't know exactly when that cleanup crew is going to come in and do their thing. Could happen at any time.
So there's a trade-off. Convenience and safety, but maybe not as much control over performance.
You got it. And that's precisely why understanding how the heap works is still really important, especially if you're working on performance-sensitive applications.
So even with garbage collection, you still got to be mindful of how your code's using the heap.
Especially if speed is a concern, yeah.
This makes me think about something I saw in one of the sources our listener sent. Embedded systems and the Internet of Things.
Right.
These tiny computers that power everything from, like, smartwatches to spacecraft, they have very limited memory, don't they?
They do. Think of it as a teeny tiny restaurant with only a few tables. Every single byte of memory is precious in those systems.
Wow. So one wrong move and you could, like, brick your device?
You could, yeah. Developers working on embedded systems have to be super strategic about where they store data. The stack, with its limited but very fast access, is often used for critical operations. And then the heap needs to be managed extremely carefully just to make sure you don't run out of space.
So it's fascinating how these fundamental concepts of stack and heap, they play out in such wildly different contexts.
Yeah.
And another area where performance is king is, of course, game development.
Oh, for sure.
I mean, fast-paced games are all about speed and responsiveness. I can only imagine how crucial stack and heap are in that world.
You're absolutely right. It's like a high-pressure restaurant kitchen during the dinner rush. Every millisecond counts. And game developers use some really clever techniques to make sure things run smoothly. One of them is object pools.
Object pools. I haven't heard of those. What are they?
Well, think of them like having pre-prepared ingredients in the kitchen ready to be quickly assembled into dishes.
Okay, I'm following.
So instead of constantly creating and destroying objects on the heap during gameplay, the game engine pre-allocates a whole bunch of objects. Things like bullets, enemies, explosion effects.
So it's like a stockpile of ready-to-use game elements.
You got it. When a new bullet needs to be fired, the game engine just grabs one of these pre-made bullet objects from the pool, sets its position and speed, and sends it on its way.
Very clever. So they're recycling game elements to avoid constantly creating new ones.
Exactly. That significantly reduces the number of heap allocations during gameplay.
Which helps to keep the game running smoothly, I imagine.
Right. And on top of object pools, they also try to leverage the stack whenever they can.
Because accessing the stack is so much faster than going to the heap.
You got it. For example, local variables inside functions. Those are usually allocated on the stack.
Okay.
And this makes memory management much simpler.
Because when the function finishes, everything on the stack is just automatically cleaned up.
Exactly. So yeah, choosing the right type of memory, stack or heap, is a key part of optimizing performance in game development. And probably in a lot of other areas too.
It's incredible how these, super fundamental concepts, they're woven into so many different aspects of software. And speaking of managing resources efficiently, how do operating systems themselves rely on the stack and heap? I mean, they're basically juggling tons of processes all the time.
Yeah, and the stack and heap are crucial to how they do it. Whenever a new process starts up, the operating system gives it a chunk of memory for its stack. That space is used to store information about function calls, local variables, that sort of thing.
So each process gets its own little private stack.
Yep, exactly. Like giving each guest at our restaurant their own separate stack of plates. And this isolation is really important for both security and stability.
What way?
Well, let's say one process crashes or starts behaving badly. Because it has its own separate stack, it won't mess up the stacks of other processes.
So it contains the damage, keeps everything else running smoothly.
Precisely. Now, the heap is a little different. That's where the operating system stores things like program code, shared libraries, and all that memory that programs dynamically allocate while they're running.
Okay, so unlike the stack, which is kind of fixed in size, the heap can grow or shrink as needed.
Exactly. When a program needs more memory, it asks the operating system, and the operating system allocates some space on the heap, like our restaurant host finding a table for a new group of diners.
And just like in a busy restaurant, the operating system has to carefully manage that heap space.
Right.
Oh, yeah. Otherwise, you could end up with a lot of wasted space.
Wasted space like.
Wasted space like fragmentation. Think about our restaurant again. As guests come and go, tables are cleared and then occupied again. But what if the host isn't careful about assigning tables? You could end up with a situation where there are a lot of empty tables, but none of them are big enough to accommodate a new large group.
Ah, I see. So it's like having all this empty space, but not being able to use it because it's all broken up into small chunks.
That's fragmentation. And to avoid it, operating systems use a bunch of different algorithms and techniques. For example, they might compact the heap, moving memory blocks around to create bigger spaces.
So like rearranging the tables to make room for those bigger groups. Exactly. It's a constant dance to optimize memory use and keep everything running smoothly.
This has been really eye-opening. I mean, we started talking about stack and heap as if they were ancient history, but they're really fundamental to how everything works.
Absolutely. And we've only just scratched the surface. There's so much more to explore.
I bet. But for now, I think it's time to move on to something we've been kind of tiptoeing around. Security.
Right. Because things can get a little dicey when you misunderstand or mismanage the stack and heap. And that's what we'll dive into after the break.
Welcome back to our deep dive. Before the break, we were talking about how operating systems use these fundamental concepts of stack and heap to manage memory and keep everything ticking along. But let's shift gears a bit now.
Yeah.
We got to talk about something kind of serious that's been lurking in the background of this whole conversation. Security.
Right, because if you misunderstand or you mismanage the stack and heap, you can accidentally open up some serious security holes in your software. Like, remember we touched on buffer overflows and use after free errors earlier?
Yeah.
I think it's worth, really digging into those a bit more.
Yeah, for sure. They sound pretty scary. And I'd like to get a better handle on how they actually work.
Okay.
Let's start with those buffer overflows.
Okay.
Those are the ones that have to do with how data is stored on the stack, right?
Exactly. Okay, so imagine you've got a program and it's taking some input from the user, like a password or a message. Now, if the program isn't carefully designed, an attacker could craft a malicious input that's longer than the buffer that's supposed to hold that data on the stack.
So it's like they're trying to cram too much stuff into a suitcase that's too small.
Yeah, exactly. Things are going to spill out.
And in this case, what's spilling out?
Data. This excess data, it spills over into the memory next to the buffer on the stack. It could overwrite super important information, things like return addresses or function pointers.
Okay, so an attacker is basically messing with the stack's memory.
Right.
But what's the worst that could happen?
Well, they could actually redirect the program's execution flow. By carefully changing those overwritten values, they can hijack the program, make it run their own malicious code.
So it's like setting up a detour, tricking the program into taking a wrong turn.
That's the right way to put it. And that's what makes buffer overflows so dangerous. They exploit the way the stack is structured. And if developers aren't super careful, even a tiny mistake can have disastrous consequences.
It sounds like there's a lot of pressure on developers to make sure these vulnerabilities don't exist.
Well, yeah, careful coding is essential. But the good news is we also have increasingly sophisticated tools and techniques to help prevent these issues. But before we get into that, let's switch gears again.
Okay.
Let's talk about that other security trap, use after free errors.
Right. Those are the ones related to the heap.
Yep.
How do those work again? Remind me.
Okay, so remember, programs can dynamically allocate memory on the heap, and then they can release it when they don't need it anymore.
Yeah, like clearing a table in our restaurant.
Exactly. But what if a program tries to access that memory location after it's been freed?
Ooh, that doesn't sound good. Like trying to eat off a plate that's already been taken away.
Exactly. That memory could have been reallocated for something completely different. Or it might be in a weird, unpredictable state. And trying to access it can cause all sorts of problems.
Cool.
Crashes, data corruption, or even giving an attacker a way to take control of the program.
Oh, wow. So it's not just messy, it's a real security risk.
Exactly. And just like buffer overflows, these use after free vulnerabilities can be super dangerous if an attacker finds them. But don't worry, there are ways to reduce these risks.
Okay, good.
Yeah.
What kind of safeguards are we talking about here?
Well, for one, some languages are designed with memory safety in mind right from the start, like Rust.
Yeah, do Rust.
It has this really strict system called ownership and borrowing. It enforces these rules at compile time, so these memory errors can't even happen in the first place.
So it's like having a super strict health inspector in our restaurant, right?
Exactly, making sure everything is spotless and everyone is following the rules. But even in languages that don't have this kind of built-in system, there are things developers can do, like techniques like bounds checking, input validation, and static analysis. Those can all help catch these potential vulnerabilities before they get into production code.
So it's a mix of language features, developer awareness, and good coding practices.
Right.
All working together to make software safer and more secure.
Absolutely. And it's important to remember, security isn't a one-time thing. It's an ongoing process.
Yeah.
New vulnerabilities are always being discovered. Attackers are always coming up with new ways to exploit them.
Feels like an arms race sometimes between the developers trying to secure their software and the attackers trying to break it.
Yeah, kind of. But that's also what makes this field so fascinating. It's constantly evolving.
And as technology changes, so do the threats and the defenses against them.
Exactly. And understanding the fundamentals, like stack and heap, gives you a solid foundation to build on as you navigate this complex world.
So this deep dive has definitely shown me that stack and heap are a lot more relevant and interesting than I initially thought.
For sure. These concepts might seem low level.
Yeah.
But they have a big impact on how software is designed, built, and secured. It's like they're the foundation of how everything works at a deeper level. And speaking of foundations,
Yeah.
we haven't even gotten into how these concepts play out in different operating systems. Let's dive into that next.
Welcome back. You know, I gotta say, this deep dive has really changed how I think about Stack and Heap. We started talking about them like they were some kind of ancient history,
Yeah.
but it's become pretty clear that they're super important even in modern software development.
They're the foundation, you know? Understanding them can make you a way better programmer.
Oh, absolutely.
We've seen how they affect everything from low-level languages to those fancy high-level ones with garbage collection, from making games to like the guts of operating systems.
And right before the break, we were getting into the security stuff, which, was kind of scary.
Yeah.
You're explaining how attackers can exploit vulnerabilities in the Stack and Heap.
Right, like those buffer overflows that mess with the stack, and those use after free errors that target the heap.
Yeah, those ones.
Those can let attackers do some pretty bad stuff, like crash programs, corrupt data, even take over whole systems.
It's a little unsettling to think that something as abstract as memory management can have such big real-world consequences.
I know, right? But the good news is that, like, awareness of these problems has grown a lot.
Yeah.
Developers are way more tuned.
Right. You mentioned earlier that operating systems also rely on the Stack and Heap. Does that mean they're vulnerable to these same kinds of attacks too?
Oh, absolutely. Actually, operating systems are often the main targets for attackers
Why is that?
because they control access to all the resources on a computer. So if an attacker can exploit, say, a buffer overflow in the operating system's code,
Oh,
they could potentially take control of the whole machine.
that's not good. Are there any ways to protect against that at the operating system level?
Yeah, there are. One common technique is called ASLR, Address Space Layout Randomization.
ASLR.
Yeah, it basically shuffles around the locations of important data areas in memory.
Like the stack, the heap, and the libraries.
Exactly. That makes it much harder for attackers to figure out where to inject their malicious code.
It's just like rearranging the furniture in our restaurant every day so nobody knows where anything is.
Yeah, good analogy. Most modern operating systems have ASLR turned on by default.
Good to know.
And then there's DEP, Data Execution Prevention.
Okay, another acronym.
This one marks certain areas of memory as like no execute zones. So attackers can't run their bad code from those places.
So it's like putting up signs that say, no running code here.
Pretty much. It's reassuring to know these safeguards are in place, but it's still a constant back and forth.
Yeah, that arms race we were talking about.
Exactly. Attackers are always trying to get around those defenses, and the security researchers are always working to find and fix new vulnerabilities. But the point is,
What's the point?
even though programming languages and operating systems are much more secure these days, you still need to understand those core concepts.
Stack and heap.
Right. It's like, even if you've got a great security system in your house, you still need to know the layout, right? Where the weak spots might be.
Yeah, so you can protect yourself better.
Exactly.
So to wrap things up, what are the most important takeaways for our listeners about stack and heap, especially in the world of modern programming?
Okay, a few things come to mind. First, don't think these concepts are outdated just because you're using fancy high-level languages or frameworks. They're still working behind the scenes, and understanding them can really give you an edge.
It's like being able to see the matrix.
Yeah, you understand how it all works underneath.
Okay, what else?
Second, always be aware of the trade-offs. Garbage collection is super helpful, but you can't just forget about memory management altogether.
Especially if performance matters.
Right. Think about how your code is using the heap.
Got it.
And third, be security conscious. It's super important to understand those potential vulnerabilities with stack and heap, even if you're not working on low-level stuff.
So you can write more secure code.
Exactly.
And just be aware of the risks.
Right. And finally, never stop learning. The world of software is always changing.
Yeah, always something new to learn.
Keep exploring, keep experimenting, keep pushing those boundaries.
Well said. This has been a truly deep dive, not just into stack and heap, but into the very core of how software works.
Yeah.
I know I've learned a ton, and I hope our listeners have too.
Me too. And remember, if you ever hit a tricky bug or a performance bottleneck, think about those basic concepts.
Stack and heaps.
They might just hold the answer.
Great advice. Thanks for joining us on this deep dive. Happy coding, everyone.